All right, so greetings everybody. So who we are, I'm Rob Brandon. I'm a security researcher with the Booz Allen Hamilton Dark Labs, and I just graduated from the University of Maryland, Baltimore County a couple months ago, where I've been working with John Seymour for the last few years on this topic.
Yep, and I'm John Seymour. I wear two hats right now. I'm a senior data scientist at ZeroFox, which is a social media security startup, and I'm also a PhD candidate at the University of Maryland, Baltimore County. Just finished my proposal.
All right, so this is just a quick overview of what we're going to be talking about today. So kind of the two key takeaways from this and the 1 minute kind of overview is negative examples in machine learning are just as important as the positive examples, which are what you're trying to detect. So when you're doing machine learning, it's as important that you teach the classifier what's not what it's looking for as much as you teach it what it is looking for. And in order to do any kind of reproducible machine learning, we need large, representative, and diverse data sets of the benign data. And for the most part, those data sets don't exist today. So kind of some of the motivation and just a quick overview of how machine learning works. I like to think of machine learning algorithms as being a lot like little children. They're very eager to please authority figures such as teachers, and for a machine learning algorithm, its authority figure is going to be its loss function. It really, really wants to make that loss function happy. But they don't have understanding of the context for why they're doing their tasks. A machine learning algorithm that's classifying, hot dogs versus not hot dogs, it really has no idea why you're trying to teach it about hot dogs. All it knows is you really, really want it to classify these things as this and everything else as this. So in order to do that task, it's going to build some kind of internal model of the world, which is basically its concept of reality. And that model is going to be constrained by the data that you give it to learn. The only thing it knows is what you tell it. It doesn't have any kind of outside understanding of human motivation or the world in general outside of what you show it. So, given some kind of a task when you are telling the machine how to do what it's doing, it can come up with some really amazing creative ways to model the data, to represent the world in order to accomplish the task. On the other hand, sometimes it can also fail very spectacularly. And usually that's going to be because the data it was given doesn't really match the data that you're wanting it to work with. In this case, the training data doesn't match the real-world problem data. So kind of a real-world example of the type of area this might show up in. So, a lot of people might like to have a bowl of M&Ms on their desk. And people being the type of entities they are, every once in a while somebody might come along and throw a few Skittles in with their M&Ms. Just kind of surprise them a little bit. So somebody might want to create a machine to go through their candy and kind of say, okay, I want to dump my bowl of candy in here, and I want to end up with a pile of Skittles on one hand and a pile of M&Ms on the other. So the way that the machine is going to be trained is you're going to hand it a bowl of Skittles. You're going to say, okay, take one out and put it in a pile, and I'm going to tell you whether you put it in the right pile or not. So you might have a pile for Skittles and a pile of M&Ms. Now say your bowl has nothing but green Skittles and all the M&M colors other than green. So it's going to pick something out. If it's a Skittle, you're going to say put it in that pile. If it's an M&M, you're going to put it in that pile. So fairly quickly, your algorithm is going to say, okay, anything that's green is a Skittle. Anything that's not green goes in the non-Skittle pile. And it's gonna work great on the data that you've shown it. It's going to be happy. It's going to say, hey, I know everything about the world. Skittles are green. M&Ms are not green. And then you hand it a real bowl where you've got all colors of Skittles and all bowls of M&Ms, and it's going to look at it and say, I have no idea how to handle this problem. And that's why the data set problem is so crucial in machine learning.
All right, cool. So we'll go ahead and talk through some of our favorite types of favorite pitfalls in data set creation. And I'm going to go through each of these in a little bit of depth. So the first is like selection bias. Everybody here has probably heard the textbook example of like a study where they're studying, I don't know, coffee consumption, and they interview everybody from a college that's right down the road, right? So nobody can really think of any reason why a college person might drink coffee differently than an average person. So we actually see this in a lot of different ways in information security. For example, if you're running a honeypot and during that entire WannaCry stuff, you're probably going to get a lot of samples that are WannaCry. That's not going to be representative of the actual entire malware problem as a whole. There's also something called capture bias, where basically you pre-format your instances in such a way that actually changes the actual problem a little bit. And so an example of this, if you go to Google and you search for coffee mug, say you're trying to create an image classifier to determine whether a picture is of a coffee mug or something else. Basically, almost every single coffee mug you'll get on Google image search is centered in the picture with the handle on the right side. And so when you build a classifier, it's going to pick up on these things. And so things with the handle on the left side, it might not actually determine as a coffee mug. And so this can actually be also seen in information security, right? If you, I don't know, neuter your malware before you actually run your data science problem on it, or if you, for example, run it through some sort of, IDA Pro or something where your analysts are actually making comments inside of the malware itself, right? If your model's actually using this extra information and making assumptions about the real world, they might not actually translate into the real world. The type of bias that we're most concerned about right now, and actually is sort of a special case of the selection bias that we were talking about earlier, is negative set bias. So what we see in information security is a lot of effort being put into finding interesting things, like, for example, malware or bad network traffic. And then when people are going, okay, we actually need two classes in order to create a binary classifier, we're going to, I don't know, just grab some Windows executables or use Alexa top 10,000 or whatever. And we're actually going to argue a lot of these simple, very simple approaches are actually not so beneficial, right? They're not representative of benign software in general or benign URLs. And we actually have a case study in a minute where we'll talk about that. And then the final type of bias that we're really interested in here is called category bias or label bias, right? So oftentimes labelers disagree on what the actual definition or what's interesting, right? Here in the tweet, like frozen water, is it liquid, is it solid? We don't know, science doesn't know. So like this happens all the time as well, right? Like if you're creating a benign data set, everybody has to agree that every single sample in that data set is actually completely benign. And furthermore, or in some other contexts, like in malware families, for example, a lot of antivirus vendors actually don't agree on what family a particular sample exists from. And so what we've been finding is like most prior work actually uses data sets that are like scraped together based on their own network or industrial proprietary data sets that can't be shared with the research community. Or they sample from larger data sets like VirusTotal, but they don't actually say how they sampled from these data sets. And all of these actually contribute to a much larger problem of reproducibility, right? It's really hard to test for these simple pitfalls. If you don't have access to the data set, you can't actually reproduce the results in the literature. An example that actually was a positive one for me, basically, there was a 2012 paper in Black Hat USA, as well as InfoSec Southwest, that claimed basically we found 7 features that classify malware with 98% accuracy. And so first off, I do want to say this was a good paper because it did explicitly say, here's our malware samples, here's where we got them, you can download them. Here's our benign samples, here's where we got them, you can download them. Here's the features we used. Here's some analysis on why those features we think make sense. But their benign set, they actually only used Windows PE files from a clean Windows install. So basically what ended up happening was this model was actually capturing on the fact that there's debug information. So when the actual program crashes, Microsoft has decided it might be useful to have some information about why it crashed. But that's not actually representative of all benign programs, right? Lots of programs don't actually have debug information, don't have debug tables. And so what we did was we went out and grabbed some other benign samples from places like Cygwin and package managers and SourceForge. And like, basically this model completely failed on these new instances, right? It got 0.5% accuracy, and it just, I think it actually broke on several of the samples, right? So we need to actually focus some on our benign data sets. And actually the earliest sort of conference presentation that I saw that like basically talked specifically about data sets and information security and some things that we actually need, CSET 2009, actually gave some guidelines on what we'd actually like out of a benign data set, right? We need data sets that adapt over time, right? If you just have your like 2012 state of malware and in 2020 everybody's still using that, then it's not going to be useful anymore because the landscape has changed. We also want something that actually other researchers can actually use, right? It's no fair if I'm just this big bad AV company and I have my own proprietary data set that I report results from, but no one else can actually reproduce my results because they don't have the amount of data or they don't have the type of data that we have, right? And then this is actually compounded, especially in the benign software case, because benign software people are writing to make money. So they don't necessarily like people just trading around benign software all willy-nilly without paying anyone anything. There's a lot of licensing issues involved. So that's another consideration that we have to solve in this sort of sense. But finally, going back to all the types of bias that we were talking about a few minutes ago, we'd like something that's sort of representative of benign software in general. And that's kind of a moving target and hard. But we're trying to sort of make progress toward that end.
So I'm just going to talk a little bit about some of the common sources of bias that we find in executable software. So just within compiled C binaries, there's a lot of potential sources of bias that aren't necessarily accounted for in a lot of the data sets or research that's out there. So one example is programmers. Everybody writes code differently. If you give two people a problem to solve, like if you tell two people to go write a quicksort, they're going to write it differently. Another area of bias is the compiler. Different compilers, given the same source code, will output different binary code. So for example, say you want to zero out the EAX register. One compiler might do a move of 0 into EAX. Another one might XOR EAX with itself. So that's a case where you're going to have two things doing the same things. It's another source where you can introduce bias inadvertently if your data set only includes code from one compiler, and say your malware code has totally different compilers. You end up with basically a classifier to classify compilers rather than benign versus malicious. And another area is optimization settings. Depending on the optimization setting, the same source code can be totally different even within the same compiler. It might decide, for example, it might decide, well, this recursive function you've got, I can go ahead and implement that as just a loop. Or it might say, hey, this function is used in multiple places, but it's a really simple function. I'm just going to inline it, and now you don't have the overhead of a function call. And that code's going to look totally different than the non-optimized code. And that's just the stuff that goes into the code section of the binary. If you look at the binary as a whole, it gets even harder. You have stuff introduced by the linker. For example, the Visual Studio will introduce something called a rich header, whereas other compilers won't. GCC has totally different resource and data sections as opposed to Visual Studio. And then Borland has something even totally different. So you're going to get a lot of artifacts that you aren't necessarily going to know are there just based off of the different tools that you use. So as one small attempt to start trying to solve this, I'm releasing a data set I'm calling the multiple architecture machine language data set. Right now it's only 32-bit PE and L files. The original intent of this wasn't so much for malware versus non-malware. It was mainly for doing code analysis, so building models of x86 code rather than models of full executables. But it's still a good start. So it contains files from Windows 10, Arch Linux, and finally, this was actually one of the best uses of ReactOS I've seen. Because ReactOS is fairly unique in that it gives you build scripts for Visual Studio, Clang, GCC, so you can take the same code and build it with multiple compilers and optimization settings. and get some good ground truth on how each of those things actually affects the code and affects your model. So unfortunately, I'm not releasing the Windows 10 executables. I did email Microsoft. They never got back to me and said it was okay to release. So this is the data set minus the Windows binaries. But really, this is just a start for the problem. And like I said, there's still a significant amount of bias if you're trying to use these full executables for a malware versus non-malware classifier. You know, you've still built with a limited set of compilers. You're still going to have, for example, some of the debug information is going to point back to the same user that it was built with. So you're really going to want to supplement your data set with some other sources if you're going to use this for InfoSec type problems. John's going to talk a little more about some of the other sources of data.
So we're looking to extend this. We've been working pretty hard at it. And so other than the above, some places that we've been looking to grab some more benign samples. So there's actually a lot of good Windows package managers, like Chocolatey and OneGet. We've already been using things like utilities like Cygwin and Putty. Ninite.com, of course, a lot of people use to download, a lot of software and keep it up to date as well. Unfortunately, we can't necessarily just release things again because of that licensing information. But we're going to try to make it easy so people can go, okay, I want to download a benign data set, where can I grab stuff? And then the final thing is actually there's this list of hashes of basically old software that that NIST has actually created called the NSRL. And there's a lot of places where you can go to download old applications. So also another place that you can go to grab benign data is actually try to grab all the data sources from that list. And unfortunately, they don't make the actual software available to download. So it is kind of like a roundabout way. But we've been working on that front as well.
So yeah, that's basically our presentation. Ultimately, this is a hard problem, and no two people are going to be able to solve it. So really, this is going to take a community effort to get behind and really start looking at how do we build a good reproducible data set, and how do we store it and maintain it and not augment it, because software is a moving target. The code that's written today is not going to look like the code that's written next year or 5 years from now. So, any questions?
Questions, wait for the next.
Yes. How are you handling packed or, packers that are used like zip or non-zip, or even harder ones like Amarillo?
So the question of packing is one that I've thought a good bit about. Right now, we're not doing anything with packing because the intent of MAML was to deal with code and functions rather than with malware versus non-malware. My personal opinion is if I was building an actual malware versus non-malware classifier, I would want to take the benign set and pack it with packers that I thought would be used in benign software so that the model isn't picking up just on packing. On the other hand, there are some packers that are really only used for malware. But that's really also I think a really interesting and unexplored question that's going to require building that benign data set in order to look at what's the prevalence of various packers in malicious versus benign software.
So the data sources you used were mostly Unix or Linux-based and Windows-based, right? Or did you use any Mac data sources or any of the Mac package managers?
So we haven't. That's something that's on the list of things to look at some point in the future. But just most of what we were interested in was just proving the concept in general.
No, absolutely. Cool. Any other questions?
Okay, thank you very much.